See, I have put up a few slides about a project I did for military engineering services. I have done some steel structures, largely industrial structures, pre-engineered buildings, warehouses, workshops. But this project was a bit interesting. It's not yet here. I need to see the monitor. This presentation is about 2 aircraft hangars, long-span hangars for fighter aircraft in some location in the northeast. I cannot tell you about the location. It's a defense project. We had special considerations and difficulties in design of these hangars. It had a very steep requirement, and we had to address issues related to seismic design. Wind was not that critical to govern the design. The seismic was, of course, I will talk about seismic design of long-span pre-engineered steel structure. It was a composite structures where the roof was pre-engineered girder resting on 2 annexes which were done on reinforced cement concrete. The 2 hangars here I am showing, the first one is called the tech flight hangar, where they maintain the fighter aircraft. And these fighter aircraft are Sukhoi 30 Mk2. This fighter aircraft, the Mk1 of course was coming fully assembled from Russia, but the Mk2 are basically, we are doing it in India now. Of course, the technology transfer has happened. So they do a lot of maintenance of this aircraft. Each of these aircraft now cost about 400 crores a piece. So they had to do maintenance of 2 squadrons in these undisclosed locations, and where they were not very much keen to make it fully in steel, considering certain, safety requirement. So initially the concept was developed in RCC, but you cannot have such a hangar in reinforced concrete. So we finally converged into putting up the roof in pre-engineered girder. The tech flight hangar span was clear 72 meter clear span with 10 meter annexes on both sides. The size of the hangar was 72 by 110 meter, which can house 2 squadrons. Like it should be able to serve 28 Sukhoi 30 at a time. And it is both way and open, both way it should open so that aircraft can enter from one side and can exit from the other. And for every sortie they take, they have to bring the aircraft for 24 hours maintenance and total check to make it fly again. The other one is a flight hangar where the maintained aircraft are kept ready for operation, and this is, the size was 110 by 60 meters. 60 meters is the clear span, and 110 meter was the kind of the length of the hangar. You can see the 3D visualization. I will show you the constructed hangars picture at the end. I have kept out the technicalities. It's not a very highly technical session. I don't want to talk about the technicalities, just few parameters that I would like to discuss for the benefit of those who are trying to design long-span structures in their projects. The hangar doors on one side, and as you can see, the span of the hangars were 60 and 72 meter. The height of the hangars were 4.5, 2 levels, that is 9 meter plus another 7.5 and 8.5 meter to create the parabolic span. So when we talk about PEB structures, the general arrangement of PEB structure is somewhat like this. Of course, when the span increases, we shift to some another form. So those forms are available. Like for this particular hangar, we decided on parabolic span, because as you know, if you can actually set up a good parabola, you can reduce the bending moment. Bending moment should be 0 for self-weight. When you are going to put up a 72 meter girder, for its self-weight itself, it is very difficult to control the deflection. These girders were 1.5 meter deep. So the self-weight itself was an issue, and we had to first work on the dead load. The entire bracing system was bringing a lot of load. The sheeting itself is bringing a lot of load. And to control the deflection, we need to work on a shape which could be, which could help us to meet this challenge for controlling the deflection. So we worked on several, parabolic shapes, and we had a parametric study, and then tried several, parabolic shape, and then the shape which gave us the minimum bending moment, so that it can, because the higher bending moment would ask for higher depth and more material consumption. So some value engineering in the planning stage was done. We tried to keep the incident angle for the wind at around 26 to 30 degree. As you all know, that if the wind incident is about 26 to 27 degree, the suction is 0. Mostly this kind of roofing will have suction as a governing criteria. So you can make the suction, wind suction 0 if you can do something at around 26 to 27 degree. Always not possible. There are other operational requirements. So we could achieve some amount of that incident angle, then parabolic shape, to do initial value engineering to optimize the cost of the hanger. So you can see the incident angle, that we set up for both the hangers, both the annexes, we try to use as the abutment. So that what we try to do, 0 bending moment if possible, and transfer, compressive stress to both the annexes. So annexes had to take that compressive stress, combined with the dynamic response during seismic was quite a challenge. I will show you how did we achieve the final design and execute it. This is the architectural plan with the annexes. Both the annexes, in the tech flight hangar, all the annexes were air conditioned. Let me tell you, in both the hangars, the cost of the structure was much less than the cost of the services. These entire hangars were fully supported by captive power, fully on UPS also, online. There cannot be power going off at any time, fully air conditions. And the fire, I will not talk about the other part, the fire safety was a big challenge, and we used fire suppression and fire safety measures both, and gas-based fire suppression was used. It was, as mentioned by the Additional Director General in the beginning, these hangars were approved by CFEs in Delhi for fire safety and other issues. So this is the second hangar. Of course, we did a risk analysis for earthquake. This location is in northeast, zone 5, for wind 50 meters per second. And these hangars are in airfield, so you're in the terrain category 1, where your wind onslaught is never there is no turbulence. It just comes and hit the hangar. So we took the maximum factored wind speed for these hangars. Of course, the last one is the geohazard map for earthquake. As you know, the entire northeast in the Himalayan region is subjected to very high acceleration, 36% of G. These are the codes we had to go. And for wind, we took this parabolic shape and tried to investigate what could be the wind pressure. And then, depending on the height, we found that the factored wind pressure was in the range of 1.7 to 1.8 8 kilonewton per meter square. And of course, we also had to look at the openings. So we created all those load cases for both side open, for one side open, and considering all the cases, we created all the load cases, and then did initial wind analysis, and we found that mostly for this hangar, entire wind pressure was in suction, and the maximum suction was applied, and we carried out some wind analysis. Of course, for earthquake, we understood that a static analysis will not be enough. What we faced during our analysis that the dynamic response was to be considered in detail. We took the soil type 2. The soil was liquefiable. That was another challenge. We actually did a composite damping analysis to find out what kind of damping we should take. It's not 2%, neither, because it's a composite structure, neither 5%, it should be somewhere in between. So we carried out a complete initial eigenvalue solutions to understand what is the composite damping of the structure. It was around 2.6% to 3%, and accordingly for every frequency, response, we applied the composite damping in that particular frequency range. We carried out a complete eigenvalue solution for the hanger. These hangers were having seismic joints. So for every segment, we carried out the dynamic analysis. And we found, you will see that I have shown the arrows, the vertical oscillation was prominent. If you look at the hanger, the most flexible part is the roof. And the roofing system was going up and down all the time. It was just prominent for first 10, 12 nodes. And even in higher frequency, it got coupled with, earthquake response in the horizontal direction, primarily across the hanger, along the span. So this was carried out. And if you look at the hanger during constructions, these girders, we could optimize up to, as I told you, about 1.5 meter. Another interesting thing was that the girder was constant depth. This particular project was reviewed and vetted by IIT Roorkee Earthquake Engineering Department. And they suggested that you cannot change the thickness of the girder, because problem was that in the central portion, usually when we try to reduce the depth, the deflection was going up. Even then, the deflection was not less than 100 mm. We cambered it up by about 150 mm to adjust the deflection after erection. So this was during erection, and let me tell you, no crane was used to erect the girders. Every girder was weighing around 14 ton. It was in a segment of about 12 meters so that you can put it in trailer. The entire roofing system was fabricated in Gurgaon and was transported to the location again through trailer and erected. Again, we also carried out at both the end, along with the the hanger gate. Hanger gate was a breeze that we did, because hanger gate cannot be suspended from the curved girder. So we had to actually create a breeze. I will show you that. This is the hanger door breeze that was erected, and which also had its own dynamic issues. So towards the end of the hangers, the dynamic response was different, and towards the central part, dynamic response was altogether different. A few basic structural issues which was suggested by the engineers from the military engineering services, and this project was a CCNA project which was continuously evaluated every 3 months by the Prime Minister, Defense Minister, and the Finance Minister of the country. There were several directives which were coming. They said cost is not the issue. Both the hangar cost 200 crores, and it was servicing 28 Sukhoi aircraft, which each one cost 400 crores. So cost was not an issue. The thickness, the cover to the reinforcement was increased by the defense engineers to consider the blast loading. The blast loading was not directly applied, but we calculated the kind of pressure that might come due to a blast. And also, we had to make the joints absolutely safe so that the joints should never be failed at any point of time due to shear. The bolting was 8.8 grade, and insulation was provided to the steel structure in case of any fire or blast so that the structure doesn't collapse. And there is a predicted failure. You will see a lot of bracings in the central portion, which was not because of wind, but these bracings were provided to reduce the slenderness ratio of the PB girder so that it becomes very stiff. And this particular, you can see we carried out, all of you carry out pre-dispatch inspection. A simple test we carried out, of course, in addition to radiography, we carried out dye penetration test in every girder welding, and we tried to see that the welding is appropriate, and if there was any problem, it was corrected by the fabricator and these girders, you can see the sizes, the scale of and these were transported, and hundreds of them to the site and erected. This corbel was designed, we did an FEM analysis of this corbel, and these girders were connected with post-install chemically anchored fastener. So fastener design was another issue. The fastener design, we were helped by 3 Swedish engineers from Hilti. We worked together, and we only just applied 16 bolt, 600 deep, chemically anchored to put the girder, and it was transferring moment to the tune of 1500 kilonewton meter in the combination of seismic and dead load. These are the installation which was happening, and you can see no crane was used, winch was used. They used derrick, 3 poles, winch was used to lift the girders, no crane. Crane was not allowed inside because of certain reason. We could use crane from outside for some other minor erection, and this was done by just to address one issue somebody's raised. This erection was done by a local contractor, and we had good planning as it was mentioned, and this was, these girders were launched. It took 1 day to launch one girder, and post-installation was done after that. This is a view taken by the chief engineer himself. He took a chopper. I have several aerial views. We took a chopper and had to go up and take, photograph. The scale was very large. You can see the corbels on one side, which is holding all these, PEB girder, each one of them 1.5 meter deep. This is some views inside. You can see the corbel. We are advised by IIT Roorkee to increase the, the corbel and to create a seat, because in case of even any eventuality, if there is a blast, the girder, even if it is get dislodged, it will not fall off, because there is a seat created in the corbel itself, which will, which will hold the girder at least even without anchorage. So it was possible to keep the girder in place and then, anchor it little comfortably, though it was very difficult. So the site has a liquefaction issue. 7.5 meter top soil was liquefiable. So we had to carry out a complete liquefaction potential analysis, design the structure for a liquefaction, post-seismic liquefaction event, and we actually carried out a hanger, pile cap and pile analysis and tried to see what will happen if the entire soil liquefies, which is very unlikely. Even then, structure should be standing. So we found that when it liquefies, when the pile gets exposed, the time period will increase. In fact, the force decreases, but we tried to stabilize the structure by designing the depth, increasing the depth of the pile and increasing the diameter of the pile. So these are some of the completed view of the hangars and some inside views just during completion. During finishing, there is a finished view from inside. This is just before commissioning. Okay, thank you very much.